Come on in and have a seat, folks. So it is 12:30. Welcome back to another day of Chemistry 401. I want to remind you about tonight's extra credit activity, 5 points extra credits. How many people plan on attending? Raise your hands. Thinking about it? I think it's going to be very interesting. I'm very excited about it. So please do come if you can. If not, I understand. We have a periodic table in the room now. Very exciting. I'm excited. Any questions before we get started? If not, then I will point out you do want this handout because it is an additional addendum to the kinetics chapter. And I had said something like, we're going to talk about slow second steps in discussion. Well, I moved that in the lecture. That way I don't have to talk about it twice in discussion. I can talk about it once. Make sure you pick up the handout if you didn't already get it. In addition, I want to talk about catalysts a little more. And in particular, we're going to start by talking about reaction energy diagrams with a catalyst. Reaction energy diagram, well, let me start with the catalyst. The catalyst can have the same or a different number of steps. Oh, sorry, I'm out of order. Technically, this is the first page, number 48. A catalyst generally uses an alternate lower activation energy pathway between the reactants and products. Occasionally, the catalyst increases the number of effective collisions, increasing A. In the end, what a catalyst does, it affects the Arrhenius equation, which affects the rate constant. There are two things you can affect in that. By far, the biggest effect is the activation energy. That is the biggest effect because activation energy is in that exponential term of the Arrhenius equation. Why not? Let's write the Arrhenius equation there. So catalysts affect one of the terms, principally the activation energy, although every once in a while you'll see mention of it affecting the A term, which is the effective collision term as well. We'll start here for reaction energy diagrams without a catalyst. We'll do a one for an exothermic with a one-step reaction mechanism. For a reaction energy diagram, you have energy on the y-axis, you have reaction progress. On the x-axis, and all reaction progress means is that on the left-hand portion, you're going to have reactants. R stands for reactants. On the right-hand portion, you're going to have products. Because this is an exothermic reaction energy diagram, energy is given off, the products are lower in energy. P for products. And we've drawn this before. We're being a little more specific about it. We're saying this is without a catalyst and for a one-step reaction mechanism. For one step, there's one hump. And that's to differentiate that from what we're about to do. Filling in a little more details we talked about last time, that at the very peak of this was the transition state complex, what I typically call the transition state. And when we were talking about collision theory last time, the transition state was at the point of collision. It was where A, B, and C form an unnatural thing, a highly unstable thing that is transitory in nature and high energy. Transition state is the highest energy thing, species. Okay, so now let's do the same thing for endothermic with a two-step reaction mechanism. love labeling my axes. I've done it the same way as I did before. For endothermic reaction energy diagrams, the reactants are going to be lower in energy than the products. And now there will be two humps, and I'm going to draw the two humps in a specific way, and the take-home message is, for each step in a reaction mechanism, there is a hump in between your reactants and your products. I am specifically drawing this second hump here closer to products as a higher one. It doesn't necessarily have to be that way. Sometimes the first hump is higher. I'll talk about what they mean in a second. But to start with, each of these humps is one of the steps in the reaction mechanism. So one hump equals one step in the reaction mechanism. One step in the reaction mechanism. Also, for each of these humps, there is a separate transition state. So, number one, number two, so two different transition states. Now, in previous examples, I've told you that the activation energy is from reactants to the transition state, and that's pretty easy because there's only one transition state. So, activation energy is right there. But now we have a two-step reaction mechanism on the left there, or on the right, and for a two-step, it is the same idea. It always starts with reactants, and it always goes to the highest energy transition state. So, in this space right here, what I want to point out is that EA, the activation energy, is always from reactants to highest energy transition state. And this is all without the catalyst. We're going to introduce the catalyst in a minute. Any questions so far? Okay. Then there's one more thing I want to say, which is if there are two steps, we talked about having mechanisms with two steps and asking the question which one was the rate determining step. And the rate determining step, or the slow step, is going to be the one that has the highest energy transition state complex. So, here, of these two, what we would say is step 2 in the reaction mechanism is the slow step. Because it has the highest energy transition state. Step 2 is the slow step because it has the highest energy transition state. And we can understand that because as we come back to this, so the rate constant, which tells you how fast the reaction is going, higher activation energies with this negative exponential will be less reaction, slower reaction. Okay. All right. Now let's add a catalyst. We've got the same two things going on here. We've got exothermic one-step mechanism. So what I'm about to do is I'm about to redraw this as closely as possible, except that I'm going to draw my curved line here as a dash, because we're going to add the catalyst. And now these are going to be reaction energy diagrams with a catalyst. The catalyst can have the same or a different number of steps in a new lower energy pathway. So I've got my dash line here. It could be one step, it could be two steps. Typically, actually, with a catalyst, it will add a step, but it doesn't have to. So with a catalyst, might be that line there. And what we could say then is that with the catalyst, now it's a two-step reaction mechanism. So without the catalyst. With catalyst, and the catalyst provides a new lower energy pathway. And I'm sure it was an accident or a typo that I do not have a period there, but that allows me to add to this sentence a new lower energy pathway from reactants to products. And these kinds of reaction mechanisms have applications to biology and enzymes and reactions going on there. You'll also see these kinds of catalysts and reaction energy diagrams in organic chemistry as well. And so this is definitely something you want to understand and keep with you as you go. Now, other way, I mean, it's pretty going to be same idea, but I want to have you with an endothermic one. I'll redraw this one. Something like that. Actually, it came out better than I had imagined in pretty much my wildest dreams. Gives you an idea about my wildest dreams. And all we have to do is now draw a pathway from reactants to products that has a lower energy way of getting there. This could be something like that. And that's what catalysts do, and those are the things you have to remember. One, provide a different pathway. Two, it is lower energy, which makes the reaction go faster. If you don't do those things, you are not a catalyst. Any questions about that? Excellent. Did I do that right? Aha. Well, my pages are a little backwards now, but now we're going to do 50 and 51 here. So let me start. And now let's talk about slow second step reaction mechanisms. slow second step reaction mechanisms. For the reaction given here, the experimentally determined rate law is rate equals K times the concentration of nitrogen monoxide squared times the concentration of oxygen. It is tempting to hypothesize an elementary reaction step that mirrors the rate law. Certainly that's the easiest thing to do, have three molecules colliding together. But functionally, that would involve what's called a termolecular reaction mechanism, or a termolecular collision, three molecules coming together at the same time. And here's the demo that goes with that. So, two molecules coming together with enough energy to react. Three molecules coming together. And it's just less frequently, it's just less likely. It happens about 1 million times less, although that's an estimate. I'm not sure that we really have a good information about that. But it happens about 1 million times less than a bimolecular collision. Plus, if you get those three molecules together at the same time, and I should bend my leg next, there you go. That's the lazy way to do it. And but then you got to worry about all three of those having the proper orientation and coming together with enough energy. So, conclusion, true termolecular reactions are very rare. I am introducing these two terms, termolecular, with three molecules or particles coming together, bimolecular, two molecules or particles coming together. To finish it off, there's also unimolecular. And it's nothing coming together, but it's one molecule on the reactant side breaking apart into two different pieces. So, one molecule. Or a particle. Oh, and can you pass that back? An additional conclusion, when hypothesizing reaction mechanisms, do not hypothesize termolecular steps. When hypothesizing reaction mechanisms, do not hypothesize termolecular steps. Question? If you don't mind doing it while I lecture, then go ahead. When hypothesizing reaction mechanisms, do not hypothesize termolecular steps. Questions about this so even though it's the easy thing to do, we won't do it. Now let's talk about the fact that it's much more common than termolecular reaction mechanisms to have a second slow step reaction mechanism. Something missing there, right? Oh, slow second step, there it is. I don't know what happened. All right, but you have it in your notes, right? Good. All right, step one, fast. Step two, slow. Good. Now let's talk about what this means. If a step is fast before a slow step, that means that this step will come to equilibrium. So for a fast first step, step one, comes to equilibrium. And we talked about a little bit about what equilibrium means. after this chapter, that's the rest of the course is equilibrium, or equilibria, if you will. But if you remember back to Chem 400, I know I mentioned, and I'm sure most do, that when a reaction is at equilibrium, what that means, and I'll put this up here, is that the rate of the forward reaction equals the rate of the reverse reaction. Rate of forward reaction equals rate of reverse reaction. Does that sound familiar? If not, only vaguely so. Well, we did say that. And now what we're going to do is, you see I've got my equilibrium arrows here. I got them out of my pocket. This one, actually, I'm going to erase that top one because that one won't be at equilibrium. We'll talk about that in a minute. What this means is that for the forward reaction, the equilibrium, or the rate constant, that's a little k, is going to be k sub 1. For the reverse reaction, k sub minus 1. So the reverse reaction has a rate constant k sub minus 1. And because this is an elementary step in a reaction process, in a reaction mechanism, we can write rate laws from both of these. For the rate of the forward reaction, we will write rate equals k sub 1 times concentration of NO squared. So that is the rate of reaction expression for the forward reaction. Esperanza?
How did we go from only focusing on forward one to now reverse one?
Good question. How do we go on focusing on just the forward to now focusing on both of them? So, and this is a special case. We're going to talk a lot about equilibrium coming up. But this is the first case where, because this is happening fast and this is happening slow, it's like this part of the reaction is finished. And when a reaction is finished, another way of saying that is that that is at equilibrium. So it has gone as far as it's going to go. And in our analogy, remember last time we talked about the analogy of the rate determining step, and we said that if I walk 50 miles and then I take a rocket the last 50 miles, that effectively my rate, overall rate, is based on the first rate of the 50 miles walking. Now we're taking the rocket first. And we get there almost immediately, and so this part of the trip is finished. And the chemical definition of finished is equilibrium. Okay? And we're going to say a lot more about this, but that's the idea. The idea is that it is at equilibrium, and that means it's finished. And the definition of equilibrium says rate of forward reaction equals rate of reverse. So it is completely new, but we will talk it to death over the next few weeks. Does that give you a little? Okay. So we can also, we're going to now do a little k to the minus 1. Times the concentration of dinitrogen dioxide. Now, dinitrogen dioxide, can anybody tell me what we call dinitrogen dioxide in this reaction mechanism? I'll give you a hint. It shows up first as a product, then as a reactant, and cancels out. That's an intermediate. We're getting down here, but the first thing we want to do is identify dinitrogen dioxide as an intermediate. And perhaps I'm getting a little ahead of myself. Remember, there's two things that a good reaction mechanism must have. One, the rate law from the experimentally determined rate law must match the rate law for the mechanism. And we have that over here. Two, the steps have to add up to the overall reaction. Let me just take a second to make sure that this adds up to the overall reaction. We have N2O2 that cancels out. We have 2NO plus an O2. Goes to 2NO2. So yes, always check in with that. That is our overall reaction for this process so far. So now, we also write, so step 2 is going to be the rate determining step because that's the step for which the reaction is slow. For step 2, we can write a rate law from that step as well. Rate equals K sub 2 times the concentration of our intermediate times the concentration of oxygen. I think that's what I want to say about this. Couple more things. Step 2 is our slow step. Step 2 is our rate determining step. And this is our rate law for the rate determining step. Another thing I'll point out is that this, for our rate determining step, this rate law does not match our experimentally determined rate law yet. And the last thing I'll point out is always eliminate reaction intermediates from the mechanism's rate law, and then see what it looks like. Now we'll solve for the rate law associated with this mechanism. And let me just check in with where we are. So the first step is at equilibrium. This is a true statement. That is an equal sign right there. The second step, which is rate determining, has the intermediate in it. The next thing I'm going to do is, because I have an equality statement or an equal statement with my intermediate in it, I will now solve step 1. For the concentration of dinitrogen dioxide. That's going to equal, well, bring the K to the -1 to the other side. It's going to equal K1 over K to the sub -1 times concentration of dinos. Next, I'm going to plug into the rate determining step. Well, now I'm going to plug in. I just wrote it first. I'm going to plug in this statement up here. I think we're getting somewhere. our experimentally determined rate law said rate equals K times concentration of nitrogen monoxide squared times concentration of O2. So at least we got our concentrations correct so far. But now we have 1, 2, 3 constants instead of 1. Now, maybe this is because I'm an engineer, maybe not. But if I see 3 numbers that when multiplied together, they're all constants, I'd rather turn them into 1 constant. So what I'm going to do, just plain old little k, I'll define as k2 times k1 over k sub minus 1. And that is our experimentally determined. Oh, no, it is not supposed to have a 1. Thank you. Just little old k. Now what I'd like to write right here is this agrees with the experimentally determined rate law. Therefore, our reaction mechanism is a good reaction mechanism. This agrees with the experimental rate law. I guess that's going to be a colon, this reaction mechanism is a good mechanism. This reaction mechanism is a good reaction mechanism. What does that mean? That means, remember, this is a hypothesis of what could be happening for this process. We are hypothesizing that it is a 2-step mechanism where 2 NO molecules come together, create 1 molecule, so they stick together, then that molecule collides with an oxygen, makes 2 NO2. It is consistent with experiment. What we would do next is we would look for intermediate. We would start looking for these individual little k rate constants, k1, k minus 1, and k2. Questions about this? As weird as this is still much, much, much more likely than 3 molecules ever coming together at once to do a reaction. Okay. Well, this is the quietest you've ever been. Does that mean it makes perfect sense, or it makes no sense whatsoever? Or somewhere in between?
Is this like that one problem number 13?
This is just like multiple choice number 13. And this is just like 2 or 3 of the problems on your kinetics 2 discussion that you just picked up. Where were we? 50. Let's do one more. These make great last problems on the exam, by the way. Although who knows?
What the last problems are.
What's that?
The last problems are.
Last problem on the exam is the tough one, let's say. The one that separates the A's from the B's. A second example, ozone to oxygen reaction mechanism. This is a nice one to finish with because at least in your notes, our beginning discussion of reaction mechanism started with this reaction. The suggested reaction mechanism is a fast first step where ozone is hit by an ultraviolet, that's Planck's constant times frequency, that's just some form of light there. Breaks ozone apart, you get oxygen molecule and oxygen atom, which then continues. What we're going to show is that the experimentally determined rate law, which has oxygen in the denominator, ever seen something in the denominator of a reaction mechanism in your short reaction mechanism lifetimes? No. So intriguing. So here's how this goes. Step one, fast. We do the same thing. We say that step one is at equilibrium. Rate of forward reaction equals rate of reverse reaction. Yes? Here? So it is a wavelength of light where its h times frequency equals its energy. Right? Because it's energy that's going to break this molecule apart. And so that's why, I guess I could write E equals H nu. Does that help? Yeah. All right. Good. Rate of forward reaction equals rate of reverse reaction. The rate of the forward reaction is K sub 1 times ozone concentration. Rate of reverse reaction, K to the minus sub minus 1 times oxygen molecule times oxygen. Our slow second step K2 times oxygen atom concentration times ozone concentration. And on the next page, we'll do the same thing we did last time. We will solve for oxygen, our reaction intermediate. So all I've done there is I've written step 1. Now I'm going to solve it for concentration of oxygen atom. And then plug into step 2. And finally, condensed terms. And get an expression that looks just like our experimentally determined rate law. Oh, no, it didn't. This O2 should be in the denominator. Question?
So you only have the reverse reactions when it's a fast reaction? Is there equilibrium?
Yes, so from a process standpoint, even though we got different results for the two slow second steps, the process is, if you have a fast first step, set the two, the forward and the reverse reactions equal to each other, and then, depending upon what happens, usually there will be an intermediate that you have to cancel out in the slow second step. And yeah, this should be enough to answer everything that we're going to do. This is the end of kinetics. We've now covered everything. So give me a minute. We're going to keep going on the next chapter. I got to pull up my PowerPoints. So that was the one chapter that we talk about that deals with time and rates. Now everything else deals with equilibrium or different versions of equilibrium. And this one, pretty much, chapter 15, deals with equilibrium and equilibrium constants, as we'll see. So the equilibrium state, in principle, all reactions are reversible. To show this, we use what I call an equilibrium arrow. I will say this, so as I put together my PowerPoints, and as you saw in the previous part of today's lecture, in PowerPoint, the arrow actually looks like this. I don't know, as long as you've got some sort of double arrow in there, I'm fine. And one point, now that the reaction is going to go both ways, the reactants are always on the left and the products are always on the right. Many reactions appear to go one way to form products, especially from Chem 400, but remember, all reactions can go either way. In fact, all the reactions we just talked about in the kinetics chapter, until that slow second step part, we're only dealing with forward reactions, and our sort of escape clause to do that was we were looking at initial rates. But even when we did that plotting, you know, the plotting that you're doing for the homework that is due Wednesday, is we were assuming that we were only looking at the forward reaction. Now we look at both of them, and we spend the rest of the semester doing that. Got a little video here. I'm not sure how the sound's going to play, but let's give it a shot. Yeah, no, hold on.
Lead chloride forms. The equation.
Let me try that again.
If a solution of lead ions is added to a solution of chloride ions, a precipitate of lead chloride forms. The equation for the reaction looks typical. If the sample is heated, the solid lead chloride goes back into solution. The reverse reaction takes place. This is an example of a reversible reaction. In the equation for such a reversible reaction, we use a bidirectional arrow.
Good. What made this reaction go either forward or reverse? What allowed it to go in reverse?
Putting energy into it.
Putting energy into it, changing its temperature. And we'll come back to that later in the chapter. That's definitely one of the ways to manipulate a reaction into going the way that we want. So, adding heat. And we will talk about this. Adding heat, which is equivalent to raising the temperature, because the temperature will change when you add it. Adding heat, which is raising temperature. That's a capital T. Capital T is always temperature. Lowercase t is always time. We will not be dealing with time anymore. So they'll all be capital T's. Raising T. Shifted the equilibrium of the reaction towards reactants. And towards the end of this chapter's notes, we'll talk more about temperature. Remember, we're defining the reactants as the things on the left now. So later in the chapter, when something shifts towards reactants, we will use the shortcut shift left. Because we are chemists, and we, with our understanding of equilibrium, will be able to control how much reactants and how much products we have in certain ways, and we will do it. Any questions about that? One more time.
If a solution
There we go. Chemical equilibrium is the state in which the concentrations of reactants and products do not change with time, and yet the forward and reverse reactions are still going at equal rates. A couple examples of this from Chemistry 400. Take an Erlenmeyer flask, put a stopper on the top of it. And some water in the bottom. We said this is the type of system with enclosed water, also called a closed system, where you could measure or establish the vapor pressure of water. What happens is, if there's no stopper in here, H2O liquid evaporates and the H2O liquid leaves the container. Once you put the stopper in there, H2O evaporates, makes H2O gas or water vapor. That keeps happening. More and more evaporates until equilibrium is established. And then equilibrium is the state in which it is the vapor pressure. So equilibrium. Would be rate of evaporation equals rate of condensation. And the reaction looks like this. H2O liquid goes to H2O gas. And you could actually write it either way. Sometimes in Chem 400, we were just interested in vaporization. And we had delta H of vaporization. Sometimes we We were interested in the exact opposite. All we're doing is putting the two together now. And so, because I wrote it with the liquid on the left and the gas on the right, depending upon the situation, you could write it either way. The only new rule is that whatever's on the left is the reactants. Another example of equilibrium that we talked about last semester was the dissolving of a salt. In this example, we're taking sodium chloride. And if you take sodium chloride, a cube or a grain of that sodium chloride solid, with no salt dissolved, there's only reaction to dissolve it. As time goes by and equilibrium is established, you get sodium and chloride ions, and the equilibrium state would have sodium chloride dissolving to form sodium and chloride ions. So this is my way of saying we've seen these reactions before. Now we're just going to be looking at them going forward and reverse instead of just one way. And I guess to complete the picture, I could even draw an equilibrium arrow showing some of it dissolving and some of it coming back. Reactions are always going towards equilibrium because equilibrium is the lowest energy state of the system. Now, I haven't mentioned this. I don't know how much I mentioned this last semester, but when I say something and then I put a box around it, that means it's important to know. And then if I put a box with 3 dimensions around it and stars, that means it's more important to know. And what I would suggest is, well, last semester in Chem 400, the underlying concept of everything for the entire semester was this battle between intermolecular forces, which were trying to draw atoms and molecules together, and increasing temperature, which was trying to, through adding kinetic energy, break them apart. And that was underlying everything that we did, whether we talked about it directly or not. This is the statement that underlies everything we're doing, except kinetics, for the, let's say this, for the next 10 weeks or so. We do have a couple other topics that we squib in right at the end. Anyway. How do you feel about this? Do you believe me that at equilibrium, even though the concentrations of reactants and products do not change, that the forward and reverse reactions are still going at the same rate? I mean, because it looks like nothing is happening. Do you believe me? How many people believe me? Raise your hand. How many people don't believe me and would like to hear more about it? Okay. Well, so let's say a few more words about it, and those words are going to be like this. It's actually not that hard to do a test, although it's hard to actually detect it. But people have done these tests before, where they take sodium chloride and they put it into solution and they allow it to dissolve. And if it dissolves as much as possible, does anybody remember what the term for the solution is? It's saturated, right? So you make a saturated solution of sodium chloride, and actually, let's note that. So dissolving, so the equilibrium situation is a saturated solution. That's a good equivalency to make. Because no more will dissolve, That's the end of that sentence, period. Okay, so let's suppose you do that, and in this thought experiment, all of the chlorine is chlorine 35. And when I put a number there, do you know what the number means? That is the mass number, right? So, and if you look at the periodic table, which today is the first day we're able to do, and you look at the molar mass of chlorine, is it 35 or is it 35 point something? 35.45, and that's because there are two relatively common stable isotopes of chlorine. Does anybody know what the other isotope is? It's chlorine 37. Yeah, you don't have to know that at all, but that's what it is. It's about 75% chlorine 35, 25% chlorine 37. We talk about nuclear stuff later in the semester, but we won't talk about exactly why those are the isotopes. Well, let's suppose you establish equilibrium with all chlorine 35. So all of the ions in here are chlorine 35. And then so that's a chlorine 35 as well. And then you pull this out. And put in some sodium chloride with chlorine 37. And there's a little cube here. If what I'm telling you is true, then we should be able to watch the chlorine 37 go into solution and the chlorine 35 come back and precipitate into this block. And that is what is observed. I don't know if that makes any more sense, but that is one way to tell that the reaction is still going even after you've got a saturated solution, is you can follow isotopes on. That's all the evidence I have. If that still doesn't help, then we should talk more about it. 3. There we go. I don't know, it's a fascinating experiment to talk about and to think about, and I'm sure it was fascinating to do at the time. It's been proven that those reactions are still going. Now let's talk about the equilibrium constant. This is capital K. I will make all of my K's just like that, and I will do my best to continue to make little k's, which are rate constants, in cursive, but you should keep them clear in your own hand as well. Kc is written in terms of concentrations for any reaction at equilibrium. Before I write the actual expression here, I will say that Kc is in terms of molarity. And if we, basically everything else in the entire course is molarity as far as concentration units go. All right, and so this is a generic reaction where little letters like little a is the coefficient, or are the coefficients. So A, B, C, D, the lowercase letters, are coefficients. Capitals are chemical species. And this is the general form of reaction. For this general form of the reaction, the equilibrium constant expression will have concentration of C, where square brackets still mean concentration, raised to the exponent of the coefficient. So this little c right here is the coefficient. And we've got chemical species as concentrations. We've got coefficients as exponents. And in fact, an even more general term will look like this. It'll be concentrations of products raised to the power of the coefficients divided by concentrations of reactants raised to coefficients. And just to be clear, concentration of C raised to the power of little c is multiplied here times the concentration of D. There's no addition or subtraction. That's Kc. Now let's write Kp. Kp is written in terms of partial pressures. For any reaction involving only gases, this reaction involves only gases. It's the same type of expression though, except instead of concentrations, we will now have partial pressures. It'll still and always be products over reactants. My product here is methanol in the gas phase, so it's going to be partial pressure of methanol over partial pressure of carbon monoxide times the partial pressure of hydrogen squared, because coefficients are always exponents in equilibrium constant expressions. Now, one of the interesting things about gases is that they have both partial pressures and concentrations. If we were to think of that in terms of the partial pressure of hydrogen and the ideal gas law, well, we can write out the ideal gas law right there. And well, all I'm going to do is I'm going to take the V over to the other side. That cancels the V on the left-hand side, and moles over liters is molarity. So the partial pressure of a gas equals the concentration of that gas times RT. That's always true for gases. It's one of the weird things about gases. We'll talk more about concentrations for other species, but gases have partial pressures and concentrations. What we can do now is we're going to establish how to get the relationship between Kp and Kc for gas phase reactions. For gases, I guess I should write and only gases. There's no equivalent thing for aqueous, solid, or liquid. I'm going to do one more step down here and then come up there. So here's the expression I have up here. Now what I'm going to do is, for each of these species, instead of writing the partial pressure, I'm going to write the concentration times RT. So partial pressure of methanol equals concentration of methanol times RT. Partial pressure of carbon monoxide equals concentration of carbon monoxide times RT. And because the partial pressure of hydrogen is squared, I've taken the whole thing and squared it for hydrogen. So mathematically, I think we're doing all right so far. Let's write this one more time, except I'm going to gang up all of my concentration terms. Not done yet, but those are my concentration terms. I have RT on the bottom, RT on the top. Those two will cancel. And I'm left with RT quantity squared in the denominator. Like so. What is that? It's all very new. That's Kc. So Kp equals Kc. Times 1 over RT squared. And that's the derivation for this particular reaction. The more general relationship where do I have space? Let me do it on the next page. What? I have a whole new page? All right. Kp equals Kc times the quantity RT raised to the exponent delta n, where delta n is going to be, well, n is moles. Difference in moles, and it's going to be moles of gases in the product and products minus moles of gases, moles of gas in reactants. For example, for this reaction right here, I have 1 mole of gas products. I have 3 moles of gas reactants. Delta n equals minus 2. And so for this particular reaction, Kp equals Kc times the quantity RT raised to the power minus 2, which is just this expression. Questions about that?
So that exponent will change, like that's.
Yeah.
Okay, so that's not a formula because it's that what
This works all the time.
that one is okay,
Yes.
not the RT squared. That's just for the specific example.
This is just right. So what I would suggest is we took an example, we derived and did it longhand to show you just how we could substitute in. We came up with a general expression, and I'll note it as such. And then we showed you that there are two equivalents. Does that help? Was that
Yeah.
cool? Other questions, thoughts? Cool. There's a companion problem. I'll work to get those companion problems up over the next few days. Now let's talk about equilibria that involves solids and liquids. Solids do not appear in K. Those are capital K. Those are equilibrium constant expressions. If a solid does have a concentration, and this is not a philosophy class, this is a chemistry class, but philosophically speaking, if it did have a concentration, it would be constant. And if you have a constant in addition to your equilibrium constant, why not just make it one constant? Liquids do not appear in equilibrium constant expressions. A liquid in a reaction is the solvent. Solvents are assumed to be pure or nearly so. Now an example. Kp equals 1.04 at 1100 Kelvin. Write the Kc and Kp expressions for the following reaction. Expressions just mean in terms of concentrations or partial pressures. Let's do both. I have two solids here. Solids do not appear in equilibrium constant expressions. Concentration of carbon dioxide, done. Kp. Done. Solids don't appear, liquids do not appear. D, write the Kc expression for the following reaction. I have a liquid. It will not appear. All the rules that we've just gone over in the last 15 minutes still apply. It's going to be products divided by reactants. Don't include the liquid. So what does appear? Not solids, not liquids, only two things. Aqueous phases and gases, that's it. And as far as even Chem 401 goes, there are no other phases. True, there are other phases, but we don't talk about them in Chem 401. So, solids and liquids don't appear, aqueous and gases do. And so far, the tricky one is gases, because they can have Kp or they can have Kc expressions. There we go. manipulating equilibrium constant expressions given the following reaction and its Kc value. What is the Kc value for this reaction? And here I'm going to draw a parallel before I do the example in the last few minutes here. And the parallel is that if this were Chem 400, right now I'd be saying every reaction has its own delta H value. And I did the same three things last semester when I talked about manipulating delta H values. And delta H values, well, when I went from here to here, what did I do as far as reactants and products? I reversed them, I flipped them. And for delta H's, what did that do to the sign of delta H? Change the sign, right? Okay. Well, let's do this one. And I'm going to call this one, just to separate it, and I forgot this in my notes, I'm going to call this Kc1 because every reaction has a Kc value, and if you call them all Kc, it's a little confusing. For this reaction, it's products over reactants raised to coefficients. Ignore solids and liquids. That's where we are so far. We are motoring. Now, Kc up here, the initial Kc value, is here. So, when I flip my reactants and products, I take the reciprocal of my Kc expression and where I've noted these in red just to be clear what my Kc is. So my carbon monoxide is now in the denominator. It was in the numerator. I have to look this value up. And I get a value of 4.8 times 10 to the minus 48. And the rule is reverse reactants and products, take the reciprocal of the Kc value. Take the reciprocal of the Kc value. I think we're going to stop there.
And this is the rule for when you're doing the reverse, right? When you're trying to find the inverse of the Kc. So I'm just trying to figure out what this rule is for what situation.
What we're going to do very shortly is we're going to flip reactants and products. And what I need you to know is that when we flip reactants and products or reverse them, switch them, the Kc value for our new reaction is 1 over the prior
It's
one.
the inverse. Okay.
Yeah.
It's basically inverse equation, and then you just inverse the actual Kc.
You got it. Yeah, and for those of you who were big fans of Hess's law last semester, we're going to come to an equivalent for Hess's law for equilibrium constants. So look forward to that on Wednesday.